fluid coding, and AI here. Today we are putting MiniCPM5 1B under a narrow local test f16 versus Q80 inside LM Studio, using the benchmark evidence from this workspace only. The surprise is simple. The smaller Q80 file did not trail f16. It landed a few points higher, while both variants expose the same bigger problem. This one run was far from clean. If you use LM Studio, this is the practical question. When a model page offers multiple GGUF downloads, do you grab the bigger f16 file or the smaller quantized one? For MiniCPM5 1B, Hugging Face lists the f16 GGUF at 2.7 GB and Q80 at 1.5 GB. That is a meaningful file size gap. What this benchmark can answer is narrower. Did the bigger f16 artifact produce a better task score here? In this run, no. MiniCPM5 1B is a compact OpenBMB model aimed at local assistance, coding agents, tool use scenarios, and reasoning tasks where small deployment matters. The official model card describes it as a causal language model using standard Llama 4 causal LM architecture. It lists just over 1.08 billion total parameters, 24 layers, grouped query attention, and a 131,072 token context length. That makes it interesting for local testing. It is small enough to run conveniently, but the real question is whether the local behavior matches the job you want it to do. f16 means 16-bit half-precision floating point. Q80 is an 8-bit GGUF quantization that stores weights in blocks with a scale. It is not full precision, but it is also much less aggressive than common 4-bit downloads. GGUF matters because it is the format used by local inference tools around llama.cpm, and MiniCPM5 has a GGUF release explicitly positioned for llama.cpm, Llama, and LM Studio, so the comparison is not abstract. It matches a real choice people make when they download a model for a local desktop setup. LM Studio is useful here because it turns the quantization choice into a normal user decision. The docs describe local model weights as GGUF or safe tensors files, and loading a model means allocating memory for the weights and related parameters. LM Studio also supports model names with an 8-tie sign quantization suffix through its CLI, which lines up with the labels in this benchmark, MiniPM5 to 1B at f16 and MiniPM5 to 1B at Q80. The point is not that LM Studio removes every variable, it makes the test familiar. Here is the headline result. f16 scored 681 out of 272 or 31.35%. Q80 scored 684 out of 272 or 31.49%. That is only a 3-point difference and only 0.14 percentage points. So the honest read is not, Q80 is better. The honest read is that no meaningful f16 advantage appeared in this one local benchmark. That is still useful. It challenges the reflex that the bigger file automatically buys a visible quality win. The category breakdown is where the result becomes more honest. Coding was identical, both variants scored 680 out of 2100. Everything else was tiny by comparison. Q8's picked up 2 points in data interpretation and 1 point in safety policy, while source research was tied at 1 point each. That explains the entire headline lead. Q8's did not win because it wrote better code in this suite. It won because of 3 1-point differences outside coding. The hard part of this benchmark is not the f16 versus Q80 gap. The hard part is the failure pattern. All 21 coding cases were marked failed for both variants, even though the evaluator awarded partial credit across those cases. Most non-coding categories were 0 or near 0. Planning operations, quantitative reasoning, and writing editing all scored 0 for both variants. Q80 also had one data interpretation case marked as an error after a 120-second timeout, so this is not a clean win. It is a narrow parity result inside a rough run. This benchmark does not prove that Q80 is faster. It does not prove that Q80 uses less runtime memory in this setup. It does not measure energy, latency, throughput, GPU offload, or stability across long sessions. The reports also do not record hardware specs, LM Studio version, exact GGUF hashes, prompt templates, context length, sampling settings, or whether MiniCPM's thinking mode was actually applied. So the safe claim is specific in this task or suite on this local run, f16 did not beat Q80. For a developer choosing what to download first, Q80 looks like the pragmatic starting point for this exact MiniCPM5 1B LM Studio setup. It is the smaller official GGUF artifact, and this benchmark did not show a quality score penalty against f16. But that does not make f16 useless. If your own prompts are quality critical, or if a failure matters more than disk size, test FCC on your real tasks. The better rule is simple: choose the quantization by measurement, not by assumption. My verdict is narrow on purpose. For this one MiniCPM5 1B benchmark in LM Studio, f16 did not earn a higher score than Q80. The result is best treated as a practical tie, with a tiny Q80 scoreboard edge and a smaller file size. But the larger lesson is the failure profile. A compact 1B model can be useful to test locally, especially around coding adjacent tasks, but this run argues against trusting it blindly for planning, quantitative reasoning, sourced research, policy, or writing tasks. If you are comparing local model downloads, benchmark the task you actually care about before you trust the file name. Like the video if this helped you read the f16 versus Q80 result more carefully, and subscribe to Fluid Coding and AI for more practical local AI and developer tool benchmarks.